So first of all, we want to pay our attention to the right triangle, right? So you guys got to know a couple basics about the right triangle. It got to have one, so a right triangle, it got to have one right angle, right? Makes sense here? And then so these two other angles right here in the right triangle, these two other angles have to always be acute angles. You see that? And so you can name this guy an alpha angle, and then this guy's a beta. We mathematicians, we love using the Greek letters for that, right? But so these are all the alpha, beta, these are all angles. I named them, and then they gotta be acute angles. That's the things you know, right? Alpha and beta must be acute angle. Acute, I mean the measurement in degrees. So when we get ourselves back into the triangle, and we're more into the traditional geometry, and we're more comfortable with writing the angle measurement in degrees, right? So anywhere from 0 to 90 degrees for that alpha, right? And the same with the beta right here. Beta has to also be, and actually I should even write just strictly less than 90 degrees, anywhere. Things to be reminded, and further, the measurement of the two angles alpha and beta added up gotta be 90 degrees. It's just the way it is. Because in a triangle, we're always going to have the sum of three angles to be 180 degrees, right? And one angle we already knew to be 90 degrees right here. So, of course, these two other angles must sum up to be another 90 degrees angle. And so now, the way how I draw my right triangle right now is sort of like a couple of terminology here. So the side that's exactly opposite from the right angle right there, you guys know the name for that, right? We've been calling that the hypotenuse. So right now I put the triangle in a way too easy so that we can easily recognize, but then be ready that the triangle can be placed kind of like in any orientation right there, anywhere you want, but point out that the longest side, right, opposite from the right angle, has to be we call that the hypotenuse. Right? And then let's say these are the two legs. There's always two legs here. Right? Okay, those two, the sides that are adjacent to your right angle, we call them the legs, the two legs. Sound good with that? Okay. So that's just basic geometry with that. Nothing surprising. I'm just briefly reminding you that, right? Let me now draw a new triangle. Okay, got a right triangle. So we got a right angle right here. And then how about let's look at this angle right here I call alpha. And alpha or beta, whatever you want to name it, right? I name it up here on my board being alpha, but you can have a different name like that. But so now, and the point here is we just be focusing right now at one of the two acute angles again. So let's say with your right angle right there, right, with this acute angle right here, then there's always a side, right? There's always a side here, the opposite. So here I call it opposites. But opposite as relative to that angle right there. See what I mean? Right. And then of course this is still the side that's always opposite from the right angle. We always famously call it the hypotenuse. Okay, so nothing to argue about that. But now I'm talking about if we put our attention on one of the two acute angles, then the side, then always the side that's opposite to that. You guys agree that? And then the side that's right alongside of that, we call that as the adjacent side. Adjacent side. Agree enough with that so far? So for this angle alpha right here, then that side is the opposite. And this side right here, this leg right here is the adjacent. Right? So if you're looking at this other angle, also another acute angle in your triangle, right? Then this side right here is now going to be the opposite side. And you see that's the reason why I'm writing that in a different ink color again, right? Because So if this angle here, the red one is what we're looking at, then the opposite side is down here. You guys follow it? And then with this one right here that we're looking at, right, then this side right here is now indeed called the adjacent. And so in that way, in the way how we have come up with a couple of terminologies and all that, right? Then just like that, your triangle can be all over. You can see you can have a triangle like this, right? Where you are given or you recognize that there's a one right angle right there. Then and now I'm instructing you to look at this acute angle, for example. Let's name that theta, for example. So if this is the acute angle theta, then who's the opposite? And let me label the names here. We got a side here being C, a side being B, and a side being A right here. So A, B, and C, which one is the opposite of this angle theta? A, right? So in this picture right here, then A is the opposite. And for short, I'll just write OPP. Okay, sounds good. Okay, and then so and relative to theta, again, which side is the adjacent? The adjacent to that? That would be what? B. Saying that. And then of course C is the length that's always opposite from your right angle, so C permanently remains. And the hypotenuse is always the longest side in any of the right triangle. Okay? And then so C here is of course your hypotenuse. For short, we write that. Okay? See what I mean? Okay, so just get comfortable with reading right triangle. So now the idea now is that when you have a right triangle, right? Think about, you can take the whole triangle, take it out from the board and put it on a circle. Now, here's my x and y axis. See what I mean? Okay? I can physically take that out, try to rotate and put it here so that it goes kind of like this. See what I mean? So that after I put it down right there, the angle that we're looking at stays right at the origin of our x and y axis, right? And then in that way, and the right angle lands right on the x axis. We can purposely do that. See what I mean? Right? And of course, I'm not an artist, so don't blame me if I cannot get the exact same picture. But the idea is, imagine that you take this whole triangle, right? Take it out of the board, rotate that a little bit so that the right angle lands right on that side like that, right? And then the angle that you're targeting at, theta, is right at the center, right? It's right at the origin of our axis. And so in that way right here, what do you see? This is the opposite, right? Right? And that was the length A right here, right? And then the adjacent is here. But A, B, and C, the way how we name that is not even important, but this is the hypotenuse. See what I mean? Right. That's the hypotenuse, right? And so in that way, well, we've learned from this is from earlier days, in earlier lecture we have already learned. You see, sine of theta, the angle here, right? Isn't it? There's always if we take the hypotenuse, the length of the hypotenuse here to be the radius, then this triangle right here stays right on some kind of big circle, not necessarily the unit circle. Right? You guys see what I'm trying to draw right there? So from our earlier days of learning it, then sine of theta, from our previous understanding that we are already hopefully fluent at this point, the sine of theta from our previous understanding, and it's going to be what? The y value, right? Because as I drew that circle center at the origin and going through that vertex right, that vertex right, then this is our point, and so it's the opposite here is acting as the y coordinate for that point, right? And then the adjacent length right here is going to be acting as the x value. You guys follow with that? Yep. And the hypotenuse turns out to be exactly the radius when we put our triangle like that, right? To stay right on a circle center at 0, 0. So in that way, right here, from our past understanding, you can now bring back your previous understanding. Right? Sine of theta, how do we call that? See? Y over R, right? That was from our previous understanding. But now if we're seeing the y, the r here relative to this right triangle, then yes, we come up with a new understanding. That means sine of theta will always be y is the opposite, right? And then the r, the radius, is the hypotenuse of your right triangle. So we have now derived it. Now in a right triangle, right? In a right triangle, the sine value is simply opposites over hypotenuse. Sine value of your angle theta, right, is equal exactly the same as the ratio between the opposite side and the hypotenuse. See what I mean? So taking your triangle out and put that on the unit circle is just a way for me to explain. It's just a way for me to explain the reason why. Right from here, right? If you're looking back at the original picture itself without a circle, now we have a formulation. Like there, that's yes. I have found out that sine, right, of this angle theta. That's right. That equals opposite, right, over hypotenuse. And then, so in that way, trust me, as I give out enough information later on, once I'm finished with giving out all of these information right here, it's going to be a lot. So keep in mind, sine is opposite over hypotenuse. Sine is starting with the letter S, right? Opposite is the O over here, and hypotenuse is the H. So a lot of time you hear people say, so, like that. Like we take the first three letters, SOH, as sort of like a quick, brief reminder when you're looking at trigonometry in the right triangle. And you hop onto to Google and YouTube websites and you come out with these all over. Like so that's for mean sines in the right triangle, right, equals opposites over hypotenuse. See, sine is opposite over hypotenuse. But you got to know which one, relative to whatever that angle is, right? Which one is the opposite and which one is the hypotenuse. You got to nail that down. That's where those so come from. See what I mean? Okay. So same triangle and same argument again. I'm going to take this away because I need more space to write it. But the way how we perceive, the way how we see who's the adjacent and who's the hypotenuse and who's the opposites are all here, right? This same triangle right here. And then again, I'm going to take that triangle just like that. I'm taking that triangle, cut it out from the board, try and rotate that and put it on the axes just like that. So that there's a circle going through that vertex point. See what I mean? And then your angle theta is being seated right at the origins, and the right angle lands right on the positive x-axis. I should have mentioned that earlier. Like the right angle falls right on the positive x-axis. Okay. So in that way, again, there's a change in the x, and there's the opposite being the y. This picture over here. So from our earlier learning, the cosine of the angle theta, right, from earlier learning, it's x, right? The x coordinate of our terminal point. Okay, so terminal point is here, and we divide that by r, which is the radius around circle, right? Or the radius, how far it makes from that terminal point over to the origin. And so in that way, right here, what do we recognize further? Now with the triangle context here, in the situation of where we recognize further as a triangle, the cosine of the same exact angle theta can now be seen as what? X is the adjacent. See that there? Okay? And then the R right here is the hypotenuse. Yeah, so ladies and gentlemen, the same exact material we've been understanding it, but now in a different point of view, right? We have discovered that the cosine, when we talking about in a right triangle, right? Turning your attention to any one of the two acute angles here, then we have found a relationship between sine and cosine, right? With relative to those sides of your triangle. So cosine of an angle theta from the right triangle, right, will always equal exactly the adjacent, right? The adjacent side over hypotenuse. Good. And so once again, back in this limited space right here, yes, we've got the final formula, cosine of theta, right? Theta here, red in cosine of theta. We want that to always be adjacent, right, over hypotenuse. Yes, we have another fundamental formula. So because of that, see, the letter C, the letter A, the letter H right here. You know? So hop onto Google and websites these days, a lot of time mention ka. So from earlier, when we were looking at vowel sign, we got so, right? Now we read these two words, so ka. You know? It's not really a word, but now these days people use it so often, so it almost becomes a word. Who knows? In another 10 years from now, right? It's become a formal word, where it's gonna have its own place in the dictionary. Who knows? See what I mean? Right? So SoCal, that's what it means. It means it reminds the people doing math or doing trigonometry that the sine is opposite over hypotenuse, right? And the cosine of the same angle is going to be adjacent over hypotenuse. Okay. And again, on our circles here, the way how I made it, the way how I have explained it, we take this triangle, cut it out from the board, right? Rotate it, and put that in the x and y system. Right? And then the angle theta that I had mentioned already being an acute angle over here, the angle theta can be the least angle is a zero angle, right? And the biggest angle has to be anywhere less than 90 degrees. Because when it hits 90 degrees, we won't even have a triangle. See what I mean? Right? And so, that way, tangent, right? Tangent of theta. What do we use to know about it? This is our terminal point here again. Once we place our triangle like that, then here's the terminal point. So, how do we know about tangent from previous learning? It's y, right, over x, right? Y over x. Right? That's what we learned from our past understanding. Because we're talking about the coordinates of our terminal point. The y coordinates, the x coordinates, the rectangular coordinates. And so tangent of the angle theta, right, at the center, that is going to be y over x. But now from that way, hey, wait a minute. In this picture, y here is simply just the opposite side, right, of our triangle that we are placing here. And then x is the adjacent side of our triangle that we are placing here in respect to that angle at the center, right, at the center of the circle. And so in that way, we recognize further that, hey, generally in a triangle, right, tangent of any acute angle, right, any of the acute angle has to be what? The opposites, right, the ratio of the opposites over the adjacent. Yeah. We recognize another relationship. Okay. So right from here, tangent of theta equals opposites over adjacent. Yes. That. See what I mean? Opposite over adjacent. And so because of that, once again, in some random day, right, you hop onto the web right there, and you may hear people use this. See, it came out from T as the first letter for tangent, right? And then O is the first letter for opposites, and A is the first letter for adjacent. So you may hear, or you may see a lot of Google websites that tell you that you got TOA. See what I'm saying now? So all three of those together now becomes one formal word, because SOHCAHTOA. Indicating that it's just a quick trick to remind you the relationship between sine, right, the ratio equals exactly to the ratio opposites over hypotenuse on your right triangle. Cosine of that designated angle is going to be equals exactly the ratio between adjacent and hypotenuse, right? And then the tangent really, that's what the T is for, opposite over adjacent. Sounds good? Okay. And so it took me some time to explain right here, but when we actually get into using it, it's going to be, you got the whole world of applications of this thing that come out again. Okay. So I'm going to switch to the other side of board. Let's do some real application. I mean, when I'm drawing this, the triangle is not drawn to scale over here. Right? Just trying my best because it's why I'm not drawn to scale. Right. But anyway, what I have here, the right angle right there, about there. See, so anywhere people want to indicate for you at the right angle, to use that little symbol, right? Then, right, like that. So how about we call it 3 here, 4 here. So these are the lengths of your those edges you get, right? 0.5. So the longer side here is opposite to that right angle. Okay? So come up with your creative name right here. Now aside from that, now stay with me here a little bit before you take notes here. But so aside from that right angle, which we don't need to name, right? You guys want to come up with some creative names to label for these two angles here? These gotta be acute angles, right? But go ahead and name those for yourself again. But let's say only one person volunteer, and then the rest gonna take that. Alpha and beta are two angles. Okay. Your triangle here, got 3, 4, and 5, right? Those are the length of those edges. Okay. So now let's calculate, or let's find the following value. Let's calculate, and I don't even want to call it part A, part B, or part C, or whatever. So we don't know the degrees for these, right? These are all completely unknown degrees. See what I'm saying now? But at least one thing you guys can calculate. What about sine of alpha? See, we don't know the nice thing about the trigonometry in the right triangle is that sometimes we don't even know the actual measurement of our angle, but there's a way for us to calculate sine and cosine and tangent and all that, right? Our angle is specifically designated here. Okay. So now in our responsibility, we need to identify, hey, if this is our angle of attention, right? We're paying attention to this angle right now, then who's the opposite? Because we always know it has to be opposites over hypotenuse, right? That's the way we always, once we've written that down as a formula, as a rule, then it's true for all triangles, right? No matter how you put your triangle, no matter how you orient your triangle over here. So now in the way how I drew my triangle, and you have chosen this angle, and here is alpha, right? And now specifically, if we want to calculate the sine of alpha, rule of thumb is whoever being the opposite of alpha, we put that over the hypotenuse. Okay, so who's the opposite? How big is the length of the opposite? It's going to be 3 is the length of the opposite, right? And how big is the hypotenuse? 5. There you go. So that means sine of alpha, right? We don't even we need to know the degrees, the actual measurement of our angle alpha. All we need is just opposites and hypotenuse, right? We're able to calculate the sine value of our angle alpha, our designated angle. Okay. So in that way, what about the sine of beta? So we're still calculating sine. And our angle here has no indication about the measurements of these angles at all, right? None of our angles here got the measurements indicated. But I want to calculate sine of beta. Sine of beta. So the beta is right here. So now as you turn your attention to beta right here, then who should be the opposite? Which length among the two lengths right here should be the opposite? Yes. 4. It's going to be 4, right? It's 4, and then your hypotenuse is 5 there, right? Yes, you found it. See what I mean? And again, it's the same rule, right? It was, my argument was that it's opposite over hypotenuse. It's just opposite here. It's different one, right? Because we're looking at different angles here, so opposite has to be that one. Right? And so in that way, we hope to fit in one more problem. What about cosine of beta? So cosine, as a reminder, for any angle, right? Any acute angle in our right triangle, right, the cosine of that angle has to be adjacent. Whoever you recognize, whoever that you can identify as the adjacent length, right? We're dividing that by hypotenuse. See what I mean? Okay. So from where beta is in our triangle currently right here, where beta is adjacent is what? Adjacent is 3 right here, right? That length right here is the adjacent. That's like 3. So cosine of beta equals 3 over hypotenuse being 5, right? 3/5. That's how you get it. So what about from right here? Cosine of alpha. Yes, another adjacent over hypotenuse, right? But we've got to carefully identify who's the adjacent of alpha and who's the hypotenuse relative to alpha here. So, do I see here? From where alpha stays, right? Adjacent is 4. Well, this 4 right here is the adjacent side of that. That's we got 4 divided by 5 being the hypotenuse, right? Right there, the cosine of alpha equals 4/5. And from the same example, right? So what about tangent? TOA over here. Tangent of alpha. What we need for any angle, right? Tangent of the specific of the specified angle is always opposites over adjacent, right? And opposite in our picture here is going to be. Let's swing back and understand the picture a little more. Okay, so now I'm looking at alpha. So alpha is right here, right? So that side is opposite. Adjacent now is 4. Right? So we just need to sometimes get used to looking at the picture. Opposites here is going to be 3 and adjacent is 4. Right? So tangent of alpha, including it, right? 3 equals 4. Okay? That's our conclusion. In the same way, we're looking at the tangent for the other angle, beta. Yes, again, it's opposites over adjacent, right? And opposite and adjacent relative to angle beta has to be, beta is here, right? Opposite is 4, right? And adjacent is 3, right? Now I'm talking about 4 over 3, which is the final answer coming out. Tangent of our angle beta. Beta over here is 4/3. So, right from the work right here, we come up with some further observation. Right on this limited space right here, I wrote down the answers, the answer for 2 little problems. Sine of alpha, right, equals to 3/5. We got the answer there. Sine of beta, in this same picture right here is 4/5. You guys following? Okay. But now here's like, so let's say you're starting out with sine of beta right here. Now, I mentioned earlier, beta plus alpha has to always be what? 90 degrees, right? Or in radians, pi/2. Beta plus alpha in radians, pi/2. You guys agree with that? Yeah? Okay. So alpha equals pi/2 minus beta. And the same thing we have, beta can be understood as pi/2 minus alpha. And so from that way right here, okay, you see how these two, sine of alpha and cosine of beta, comes out the exact same answer right now? Okay. I erased all of those minor work there earlier, but purposely leave behind those final answers here. So these two, I connect them with the double arrow right here. I just want to point out that sine of alpha being 3/5, cosine of beta being a 3/5 as well, right? So they are equals answer. So in that way, I'm seeing, yes? I'm seeing in the right triangle, sine of alpha, right, equals cosine of beta. But then writing it like this, if we're not talking about the triangle, then people have no clue what we're talking about. Because who's alpha and who's beta? But now keep in mind from our triangle, we derive the following. Yes, cosine of beta, but beta can be pi/2 minus alpha, right? Because the idea is beta and alpha must always be added up must always be summed up to pi/2. So the way I'm seeing it, sine of any angle is the same as pi/2 cosine of pi/2 minus that same angle alpha. This was our beta previously. You know what I mean? Okay. And so that was our beta here, but primarily we want to be looking at this version right here. So this is a relationship between these two. See, sine and cosine right here, we call them there. These are co-functions. Co-function. Identities. Now, as far as the example we've done, from that example, we pointed out the idea about the co-function identities. So just like that, I'm going to take away this. Okay. Cosine of alpha equals 4/5, and sine of beta also equals 4/5. And so I can see that from that relationship, I can see that cosine of alpha equals to sine of beta, right? Beta. But beta itself is famously understood as pi over 2 angle, right? Pi over 2 minus the angle alpha. Yeah. So that gives me sine of beta. Now it's substituted by pi over 2 minus alpha. So we come to another co-function identity. But cosine of any angle alpha would be equal to sine of pi over 2 right, minus alpha. So on any angle, the point is we try to write the same. We try to write that on behalf to the same angle alpha or the same angle beta, whatever. But these are the two co-functions together. Okay. So we found two co-function identities. Cosine of any angle equals sine of pi over 2 minus the same angle. Okay. Those co-function identities will become useful at some point later on. Now we're looking at our example 2. Okay. So we got an angle right here being 20 degrees. The angle space is too small, so I have to write it outside and point an arrow to it. So 20 degrees is here. Okay, and then there's the right angle right there. Got this side here as being 7. Okay? Then let's find the unknown. So we got the C right here being the unknown, and we got B right here being another unknown. Okay? And then we can also calculate this angle beta. That's also unknown. Okay? So our instruction for the problem right here: find the unknowns. We got quite a few unknowns information here, right? We got this line right here being the hypotenuse, that's unknown, right? We got this line right here being one of the two legs right here, that's unknown, right? And then this angle right here that my arrow is pointing to, this acute angle right there, I call it beta. Got 3 unknowns in this problem. Let's find them out one by one. And so here's how I'm seeing this. Well, from this angle that we know being 20 degrees, right? Now with a known measurement being 20 degrees, you can calculate easily using your calculator. But make sure to put your calculator in degrees right here, because our angle is measured in degrees, right? So sine of 20 degrees, we can get this out of the calculator. You guys agree? Okay. But then on the other hand, from what we have just learned, right? Sine of that, wherever that angle we call 20 degrees right here, sine of that has a relationship with these lines right here. This is opposite, right? This line that we call being 7 is opposite hypotenuse is the line C right here. Right? So that means what? Right now, sine of 20 degrees, we can easily calculate that with a calculator. But on another hand, it equals to opposite 7, right, over hypotenuse, the unknown hypotenuse C right there. You guys with me on that? So Sine of 20 is a known value. 7 is a known value. We need to calculate here the unknown c, like the hypotenuse for our problem, right? So that means we can rearrange. This equation a little bit, multiplying both sides by c. I'm looking at c, right, times sine of 20 degrees, right, and equals 7. So we're almost there. We're solving for c, keep in mind. So now I'm going to divide both sides by whatever that will come out. So your calculator, again, as a reminder, your calculator should be able to give you 20 degrees, sine of 20 degrees, right? So now once we have that value as a known value, we're going to divide it from both sides of our equation. Right? So I decide to hold on to all of the calculation until the very last step here. Right? These sine of 20 degrees are canceled away on the left-hand side, right? So C, the unknown like we're looking for, will equal to 7 over sine of 20. So now you have a setup that we can completely handle over here with our calculator. So again, make sure your calculator is in degrees mode with that. But the way how you're typing it in, you gotta go 7, right? Slash for dividing, right? And then you hit sine right here and then type in 20. Close your parentheses and hit enter here. But remember, keep your calculator in degrees. That's what we need. Yeah. My calculator, it came out 20.466 and a lot longer than around at 2.47. And then now, from where B is, there are a couple options right here. We can go, B is one option, we can go with the cosine of 20, right? Equals the previously found value for C right there. I mean, B divided by 20.47, right? That's one way we can utilize that. So B here is 20.47, and we multiply that. With cosine of 20 degrees. And again, cosine of 20 degrees, we can calculate that out from our calculator. That's one way of getting it. Alternatively, for B right here, we can also use tangents of our known angle, 20 degrees. Right? Tangent works on your calculator too. Tangent can be equal to, now on a right triangle, right, opposites over adjacent, right? Opposite over adjacent. So that can be making it a lot more direct for you. And I prefer this route actually a little better. So opposite 7 over adjacent, which is the unknown. And so adjacent here is going to be 7 divided by, or B is 7 divided by tangent of 20. Right? 19.23. I round to 2 decimal places, but it's not the rule of it. It's not always 2 decimal places. So make sure you watch out with rounding requirement. Okay? And it looks to be consistent because this line right here was a 20 something, and B needs to be a little shorter than that, right? So the two answers here look consistent with each other. See what I mean? Okay. So you found the other two unknowns. So what about beta here? Beta is simpler than what we thought. The unknown beta is simply just what? No, beta is the 90 degrees total, right? We're subtracting 20, right? Because 20 and beta must add up to be 90 degrees, right? The sum of beta and that angle 20 degrees right there got to be 90. So now to find beta, which is 90 minus 20, the known angle, that comes out 70 degrees right there. That's beta. So that's how we can use a trigonometry in a right triangle to go from a couple of known information, right? We go to find the unknown values again. All right, let's do some more apply examples here so that you can deal with more experience. So let's look at an example like this. And these examples, I'm not going to number them because they're just some of those independent examples again. So how about instead of wording it, allow me to describe something like this. Let's say there's a man standing on the ground right here, right? Okay. He is from where he is, you can measure that from where he is to a flagpole here, right? There's a flagpole over here with an unknown height. We want to know how high that flagpole is. So we call it as the x distance. See what I mean? Okay. And then from where the man stands over here to the foot of the flagpole, yes, that distance is there. It's because we can walk there from there to the pole and we measure it, right? So you guys want to name a number? Name a number. 10. Okay. 10 feet. Sound good. So the flagpole here, how tall, how high that flagpole is, we don't know. But then this man he got a measurement. So from where he is, right? There's an angle. We call this angle over here, as far as just the terminology, it's called the angle of elevation. Because we're looking at, see what I mean? So it's called angle of elevation. So from the foot of the man, the angle of elevation here, let's say theta, I'm going to call that, how about 35 degrees? See what I mean? Okay. So simply in that picture right there with my explanation. Now you want to say, okay, how tall, right, or how high is a flagpole. Right? So this is where we can see that some of our applications where we apply trigonometry right out there in our daily life with them. Okay. So the idea now is that when you're seeing this, see right here in the picture I'm drawing, it has to be, it's a right triangle, right? Right triangle, and from where the foot of that flagpole is, it's a right angle, right? And so our angle theta right here is some acute angle, as I explained earlier in the main lecture over here. So, and we got to know measurement 35 degrees. And so from our understanding from the main lecture, this is the length of our flagpole right here, how high that is relative to a triangle like this, and we call it as the opposite side of the angle, right? This is where the angle is. This x length right here is the opposite side. You guys follow with that? And then this 10 feet distance right here from where the man is to the foot of the flagpole, that's the adjacent side, right? So in this case, we want to find the value for x. So we got one direct axis right here. Don't we know from our previous learning from the lecture that tangent of the angle, so you see the angle is 35 degrees, right? So tangent of 35 degrees, you can easily calculate that through a calculator, right? The tangent of 35 degrees will equal to, what's the rule here? Opposite, right? Quick scratch here, opposite over adjacent. TOA, remember TOA, right? TOA, right? Tangent is opposite over adjacent. And so in that way, yes, tangent of 35 degrees can be easily calculated with a calculator. But then on the other hand, we want that to equal, now I'm going to erase this, right? And really put in the actual expression. We want that to equal x over 10. See what I mean? Okay. And so from here, we have a relationship where we have tangent of 35 degrees is a known value. 10 here is a known value, x is the only unknown, right? So we can easily multiply tangent to the other side. So making it x equals 10 multiplied with tangent of 35 degrees, whatever comes out from tangent of 35 degrees from your calculator. Okay? So now go ahead and use your calculator with that. And make sure to turn your calculator in degrees mode with that, right? And then we run tangent of 35 degrees with that. So that means what the flagpole that we're looking at here, right, being 7 feet tall. Any questions for me on that? So what we have here is a triangle and with two sides. One of the sides here is 191, right? And then the other side here is 223. So these are the sides. And so there's the angle between right here, we call it, the angle between here is 123 degrees right here. So we call this angle, in common term, we call this angle the included, right? Included angle. Okay. So in case later on, when you guys are sometimes being given now the description of the problem, it worded. So you got two sides of your triangle, right? Two sides of your triangle is given to be these two measurements, 191 and 223. And then the included angles, that means you just automatically have to know that the angle between the two given sides, right? The included angle is 120 degrees. But then from that, we want to find the area of the triangle. Why I put the plural on this angle over here? There's only one included angle. Right? The included angle between the two sides. And any two sides in a triangle, needless to say, is always the consecutive of each other, right? Always adjacent with each other. Okay. Now we want to find the area. All right, so getting into the problem right here, here's how I'm seeing it. The triangle itself is not a right triangle, right? It's an obtuse triangle, as a matter of fact, when we're using that term from basic geometry. But in the end, for any triangle, see, when you have a triangle like that, for example, right? Calculating the area, you can do, see, altitude, right, times the base, that's one way. But you can also do this. Altitude can be from this vertex down to the other side of that. See what I mean? Right. So you can go with that, being the altitude, and multiply with this base. Or you can go with that altitude and multiply with this base. There are so many ways you can draw the altitude in respect to the base. Because three sides of your triangle, you can always treat each one of your three sides here as a base. And then from where the base is, you drop from the vertex, from the opposite vertex, a height, right? Drop down to that base again, we call that as the altitude. And so in this case here, if we go this route, and it's not a good plan, right? Even though it's the correct plan, but it's not a good plan in the sense that if we go that route right here, treating this length right here being our base, then we don't know the length there. You guys agree? Okay? And then also we don't know we have no clue to find out how high that altitude is. So we got two unknown information. So that route is not a good route. So we can turn our attention to another planning right here. So I'm just showing the planning. So we can we pick that right here. We have 223 here as a known planning, right? So we can use that as a base. So from that base right here, I can easily I can draw that altitude right from that vertex down here. The angle here is 123 degrees, right? And then this other side right here is 191. So think about it. In the road, just now in the way how I drew that altitude, and we gotta have a right angle right there. You guys would be on that? Okay. So if the angle here is 123, can somebody help me calculating what that angle is? See, the whole thing here is 180, right? So 180, take away 123, right? That will give me the angle which is right between here where my arrow points to. So in that way right here, that would be what? It's about 57 degrees for that, right? So after that quick little brainstorming work right here, we know that angle here got to be 57 degrees. After that work, I explained it again. So after having that angle, so now even though this part right here I'm drawing with dotted line means it doesn't necessarily exist in the picture, but we can use that for our problem right here. Think about from where the angle being 57 degrees right here. Right? Then this unknown altitude right here of your triangle is going to be the opposite, right? And then the hypotenuse is here. You know what I mean? We can easily calculate altitude. Will be the opposite of that right triangle. And then hypotenuse is here. So I'm talking about sine of 57 degrees. We can easily calculate this from the calculator, right? And then that equals to opposite sine over hypotenuse. Okay. And so, thinking further in terms of that means we're looking at sine of 57 degrees will be equal to, in this setting right here from this triangle, and we're looking at the opposite being the unknown length, right? That's the altitude. Let me label that. The height of that. The altitude a lot of time gets the letter H. Okay. So the height divided by the hypotenuse here is already with a known length, 191. Right? So now we come up with an equation where there's only one unknown, and we can calculate easily, very similar to the other examples we've done. Now looking at 191, if I multiply to the other side, multiply with the sine of 57 degrees, and that equals h. Right? So the plan here is to get the altitude h. So 160.19. So that's the length of your altitude, right? But now getting the altitude is not the final answer. The final answer here, we want the area of the triangle. How do we get from there? Now at this point, the area of the triangle, 1/2, right? Base times the height. Right? We already have the base provided, 223. The height we just now calculated gave 160 over here. So 1/2 times base 223, right, times the height being 160.19. We multiply it all together, we get the area of that. And whatever the units for these lines here, the unit was given in feet or centimeters, whatever, then that's going to be feet, square feet, right, or centimeter, the square centimeter. So, like I said, the units here. We just, if it was, I didn't really label the units here, so if it was feet here, right, then it's going to be whatever that is, square feet, right? And or if I label that inches here, those are inches. If that was so, then these are square inches. Right? That's how we got the area of that triangle. All right, so as another example over here, let me bring in a triangle with a picture like this. So just a little bit of planning right here, but x can be, x here as a length, right, belongs to this triangle over here. See what I'm saying? Or you can see that x here is playing in the role of the hypotenuse of this triangle. But then in the end, this triangle here, there are so much unknowns about this triangle other than that angle here is 72 degrees. See what I mean? This other triangle here has, fortunately, more information. There's the angle measurement already given, 55 degrees. And there's this line here being 57, right? And then the other unknown length, from this other triangle over here is now acting or playing in the role of the hypotenuse for this right triangle. You guys see that there? So from this angle that I'm looking at, that I focus at, now we have opposites, right? And we can, from there, we can go relating that with hypotenuse here. See what I mean? Right. So there's this unknown line we see, it's just a style, but we can also easily label that H. Some unknown that we need. Alright. So yes, our ultimate goal is to find out the length for x, but before getting there, how about let's find out what h is. So, either way how I'm seeing it, from where this angle is, we got, like as I mentioned earlier, opposites, right? And then we got an unknown hypotenuse. So opposite with hypotenuse, that means what? Sine of the 55 degrees angle, which we can easily calculate from your calculator, right? That equals to, as a ratio of the right triangle, equals opposites being 57 over hypotenuse, h, right? SOCA, right? So, sine is opposite over hypotenuse. And so, from here, I can rearrange my equation, and keep in mind again, the quantity sine of 55 degrees is a known quantity, right? It's just we didn't pull out a value yet, but it's just a matter of punching it into the calculator. So having this known value and this known length 57, I can rearrange this equation to make it h, right, equals 57 over sine of 55 degrees. See, I multiply the h to the other side, right? And then meanwhile, at the same time, I divide both sides of this equality here by sine of 55. That's how I rearrange my equation like that. And so now we have a setup that's easy to calculate for us. I need an answer for that. Alright, so from your calculation, what do we have here? 69.58, right? That's reasonable. It should be larger than that value, right? So that's how we can also check for consistency of our calculation. So that's our h. It's not the final ultimate goal yet. But now, once we have 69.58, right, right here, well, you're all welcome to filling it in, right? Fill it in 69.58, right? So now, think about it. With this angle currently in 72 degrees, we are going to see the 69.58 as the opposites, right? Now we have a known opposites relative to that angle 72. And then the hypotenuse here is once again still unknown, right? We remains unknown. So now I'm looking at one step further. Sine of the 72 degrees angle will be the unknown. Now 69.58 is the known opposite side, right? We divided that by the unknown length x, okay, which is the hypotenuse of your triangle. Okay. So now I'm going to rearrange the equation here just like how I have done that with the earlier step. So x can be calculated by 69.58. We divide that both sides by sine of 72 degrees here. These are all known values, and just now a matter of putting it out of the calculator. Go ahead, help me out with that. 60. Right, 17.60. Now this is how I can check for consistency with you. I don't have a calculator up here, but at least with a calculation like this, I can see that it's better be bigger than this, length 69 something, right? Because it's a hypotenuse. So the hypotenuse has to be the biggest length in the whole the triangle, okay, in the whole right triangle. So without having a way to precisely check, but at least I can see it's consistent. Okay. Does everybody else agree with that? Okay. Right. So that's how we're doing the calculation. Okay. So every problem here has its own way how we apply our understanding, but we're all circulating around the use of the trigonometry in the right triangle. Right. Sine is opposite over hypotenuse. Cosine is the adjacent over hypotenuse, right? And the tangent is opposite over adjacent. Right. It's so controlled. So here's the surface of the ocean. Okay. There's a lighthouse. Okay, with that right there. So there's a ship. Okay. So from where the lighthouse is, there's what's so-called the angle of depression. Meaning, think about where the lighthouse is, horizontally speaking, it projects light out like that, right? And then there's a light ray that points down like this. So there's a light ray that points down to hit the ship on the ocean right there. Okay. So this angle right here is called, in common term, in daily term, they call that the angle of depression. How things go, depressing down. So angle to look up, we call it angle of elevation, and then the angle that for something that points down like that, right? And it's called the angle of depression. So depression here means compared to the horizontal line like that. See what I'm saying? No? Okay. And so the angle of depression here is given to be 14 degrees. Now, again, forgive me that I'm off scale and all that, right? I'm not necessarily on scale right here. So that angle of depression is 14 degrees. The lighthouse is known to be 199 feet tall. Okay? And the ship is here. So the question is, I'm going to label that this distance, right, x, from where the ship is to the base of the lighthouse again, that's unknown now. That's the distance from the ship, right, to the base of the lighthouse. Alright, so that way, we just want to calculate how far that distance is. Find x, how far that distance is. And so right now I'm describing the problem completely geometrically, right? Completely with a figure over here, but be ready to read these descriptions over here in words sometimes when you're exposed to different assignment problems. Okay? So x right here is the distance from the ship, right, to the base of the lighthouse. Okay? So right from this picture, do you see a right triangle? Right here, right? See what I mean? The lighthouse itself has to stand straight up, right, from the ocean surface, okay, perpendicular to the ocean surface, to the water surface. So think about it. From that setting right here, I can extract out a picture as following. See, there's a right triangle, right? This is where the ship is. the base of the lighthouse is here. This is the unknown x. Length x right here, 199 feet is for that, right? But then the angle of depression is unfortunately kind of like out here being 14 degrees. See what I mean? Right. So in this picture right here, think about it from high school geometry, right? From basic geometry that we learned right here. Then these two lines, the base of this base actually of your triangle is supposedly parallel with that horizontal line that I'm drawing in dots. And so in that way, the angle here, so think about it, that means the angle from the ship right here, we call this angle here the elevation angle. The elevation angle from the ship. Same angle, same measurement with the depression angle, right? From the lighthouse. See what I mean? But this angle here is now also known from basic geometry. That's the same 40 degrees. Right? That's the argument that we can use. Are you understanding with my explanation right now? So now in that way, you got so from where the ship is, right? The angle of elevation now is 40 degrees, right? 199. There's actually here the unknown distance from where the ship to the base of the lighthouse. So now in that case, I'm talking about tangent of 14 degrees, which is a known value. Right? Tangent of 14 degrees will equal to opposites over adjacent, right? TOA, tangent, opposites over adjacent. So we're looking at 199 as opposites over adjacent being x. Right. So now in that case, I'm going to rearrange this equation here. I'm going to multiply x to the left-hand side, and I'm dividing both sides of this equation here by a tangent of 14. Right? So that I'm going to leave behind x equals 199 divided by tangent of 14 degrees. All right. Right, so you came out with 798.15. It looks consistent. And we can confirm with each other with that. Anybody else agree with that? That final answer 798.15. I have another prop right here. It's pretty fun for everyone. So once again, look at the picture of it. Rearrange to read the worded description sometimes. But let's say here's the ground, right? You guys know what a water tower is? Okay. So there's kind of like a water tank, ball shape, something like that, right? See what I mean? So this water tower is 300 feet away from a building. Okay? Building, windows, right? See what I mean? Okay. So, so the water tower is 300 feet away from the building. And so think about there's a man standing in one of the windows here, right? There's a man in one of the windows here. Right? If he looks from where he is, from where his window is, see what I mean? From where his window is on the building right here, if he looks to the top, of that water tower, then of course, compared to the horizontal line right here, then there's an angle of elevation. You guys see what the slide working like that? So that angle of elevation is, again, forgive me if I'm off scale or anything like that. And then from where he stands, from where his window is, right? If he's looking down to the foot, right? Then there's another angle. What we call it, remember that angle right here? Compared to the horizontal line, and then this angle here is the angle of depression, right? It's 20 degrees. And again, please forgive me that I'm off scale and all of that, right? Sounds good? So we want to find out the number one thing. How tall is this? How tall is this water tower? And then also from where the man's window over here, how high is it above the ground? That's called Y. want to find x and y, how tall the water tower is, and how tall how high that window is above from the ground. So the situation can be all together described in a picture like this. Is that a known length there, right? Is that a known length? X here. So at some point here, right? At some point here, horizontally, we got an angle of depression, right? That's 20 here. You guys follow it? Right. And then there's an angle of elevation right here. That's 42. You guys agree there? Okay. And then from here, there's a line drawing down right here. That's length y. Okay. So we want to find y. We want to find x, right? And this length right here is 300. See what I mean? So from our understanding, then here's the thing. It's gonna have to see, even though I'm leaving this dotted line right here, but it's acting as one leg of a right triangle. Because right here we got a right angle. That horizontal line is drawing straight over to the water tower's height like that, right? And that's a right triangle. But then that's not telling us much. We don't know this how long that is for this hypotenuse of the right triangle is. We don't know what that is. That distance here is known to be 300 feet, because it's the same with how far that distance away from the tower, right? So it should be the same distance here. See what I mean? So we can do a couple things for here. So now, first of all, I see that from the information we have for here, and you have to understand that x is the total length here, but this little length that I'm putting curly braces is also the same as y. From that picture. See what I'm trying to explain with that? So it's easier to find out y first, because we got more information here. We don't know this length, but we know this bottom length right here, being 300. We don't know the hypotenuse, but we know that we need to look for this unknown. And further, we know that this angle here down here has to be 20 degrees. Same argument. These two lines are parallel, right? And the angle of depression we've stated earlier is 20 degrees. So from high school geometry, we know that it's got to be equal measurements here. So now I'm talking about the first thing I can do. Opposites over hypotenuse, right? Actually, no. Opposites over adjacent. So you get tangent. So tangent of the 20 degrees angle can be found by, can be equal to y, which is the opposites over the adjacent, 300. So that means we can solve for y here by doing tangent of 20 multiplied with 300. 300 times tangent of 20. Right? So go ahead and multiply it out and help you with your calculation with that. Okay. Your calculation came out 109.19. Okay. So we got y. And that's one of the answers. Right? That's one of the answers we're looking for. Now we want to step forward and find out the whole x. So but keep in mind, x is just the total of y and something else above up here, right? See what I mean? So in this picture right here, if you now focus to this picture that I'm drawing, we already had a known length being 300 away. We got an angle being the 42 degrees, right? 42 degrees elevation angle, and then that line right here is 300. And so what matters is we find this unknown length. See what I mean? And then let's name that. Let's give it a name, like the unknown there. Let's call that some t, like that. So keep in mind that x will be the y plus t. Right? Y was 109.19, and t is the unknown we're about to find out. So this length t right here is going to be the opposite. We already had adjacent, and we know the angle. Right? So another word comes out just like that. Similarly, tangent of 42 degrees will equal to opposites, meaning t over the adjacent 300. So in that way, we can calculate. Right? So t can be calculated by 300 multiplied with tangent of the 42 degrees angle. So now all you do is just come out with a final calculation. Go ahead and help me out with that. 0.12. But now that's not the final answer, right? The final answer here is x, right? So x equals 109.19. We add that with 270.12. Right? And that, whatever that is, that will be our final answer. Okay? And we can just leave that there for you guys to complete the calculation. That should come out to be 379, right? 0.31 there. That's our final value for x. All right. So that's the different applications of of how we apply trigonometry in a right triangle. And there are other applications as well, but unfortunately we need to learn more additional understanding before we can get to those other applications. So wait until we learn some more trigonometry.